All right, you're talking my language. We have a vote from t equals 0. So let's pull this thing up. I'm going to write these things down. Got to find my pen. All right. According to the Calvinator, whoopsie. This is what he's got going here. T and some x, y coordinates. Now, by the way, if you have a quick way to do this, you're going to tell us about it because we need to know. We have a vote for t equals 0, and at time equals 0, I'm kind of curious where it hits. I can go to my calculator and I can tell you where it is at time 0 because I got a table. When I put on t equals 0, it hits the point 41. Okay, so I'm going to go back. We're going to take a look at this. 41. And I could have done that without actually using the table, right? Because I could have put 0 in both of those. It would have been pretty easy. But yeah. So anyhow, 4-1 at time 0, which means over 4, up 1. You are definitely in quadrant 1 at that time. Now, the question is, was it in quadrant 1 before that?
Yes.
Yes. How far before that?
It was in quadrant 1 when t was negative 3.9. But then, like, it's at t equals negative 4, it's 0, 5.
Ooh.
Does that count as quadrant 1 since it's on the line?
This is a great question. So t equals negative 5, you said?
Yeah. No, at t equals negative 4, it's at 0, 5.
Okay, t equals negative 4. We're at 0, 5. Are we on, now I'm going to trace, uno, dos, there we go, trace, and then you go left. You move yourself around on there, and you notice in trace mode on parametric, gives you the time. I love that thing, it's so cool. And it kind of lanes you, and so I'm going to confirm what Calvin's saying, because I'm a skeptic. Hey, he's right, negative 4, I land on 0, 5. Is that, does that count? So, is that quadrant 1? Or is it quadrant 2? Is it both? What do you think? What's your vote? Yay, nay? Quadrant 1? The question is, come on you detailed people, is it in quadrant 1? We have a vote for yes.
You have to say greater.
Oh, like greater than, like by any small amount, it'll edge itself into quadrant 1? Now that's what we're talking about. Negative 4 is the threshold. Could be in either one. So anything a little bit bigger than negative 4, totally lands in there. Nice job. So do you think there's a shortcut to that? You're right, negative 4 is where it starts. You could trace all you want and make that happen. That's fine. That's good logic to make that happen. So it starts at negative 4. I'm going to plot the point. Okay, so I'm all about the logic on this one. 0, 5 is right there. And we know that's t equals negative 4. Bingo. So 0, 5. Bingo. And time is negative 4. Clever. And you're saying it is, write your parametric values in interval notation. So t needs to be between negative 4 with a parenthesis, which is another way of saying like greater than but not touching, right? Now, where does it end? And if you have a shortcut, I want to know that too. Is it still in quadrant 1 at the end of the interval? Are there any breaks in between there? Any time when it's not in quadrant 1? You want to mention?
When t equals 1.
What happens at t equals 1?
It's at 5, 0.
Oh, no. So that's not in quadrant 1. So that means that's this one right here, 5, 0. Darn it. So 5, 0. That's when time equals 1. So that's not in the first quadrant. And remember, I'm looking at my graph. I'm going to go over there and say, Tracy, Tracy, trace, go trace. There it is, time 1, 5, 0, bingo. On that quadrant, so I'm using that. So we're going to have to go negative 4 until 5. That's a t that works. So let me show you what I'm writing. Negative 4 to 5. And do you remember the old union thing? Because that's a possibility. It's all in the quadrant there, and then it's from 5 until the end of the interval. Let's just say you kind of see that it just keeps going. You don't write to infinity, because we're stopping at 7. So we're going to go 5, 7. And it includes 7, our sole bracket. Because at time 7, it really is in quadrant 1. Totally includes it. What do you think about that? Erica, what do you think?
Why did you put 5 instead of 1?
Because I'm ridiculous and I have good people to fall back on, like you. Because I'm putting in times, right? Am I putting in x's or times? Times. That's why the t's out here. Thanks, Erica. Yes. Thank you for putting that in there. That's slick. So those are the times that work. Does anyone yet see a little bit quicker way to make that happen? We could cut to the chase. It's possible. I don't want to take that good logical process away from you because it works, but it's a little tedious. Do you notice it's those roots that that's where it happens? Those are the questionable things. We can find those pretty fast. I mean, let's look at this. If I want to know when x equals 0 so I can get a y-intercept, well then just pick the time that makes it 0. So if I want to hit the y-axis, I could pick t equals -4 and it'll make x equals 0. And then I could tell you where it hits, put 0 in for the other. It's the same time thing, you just plug it in. So if you set this equal to 0, what you're going to get is your y-intercept. Because it's like you're on the axis. Pretty cool. And you can plug it in there. So that's where -4 comes in. So t equals -4. That was our threshold. And then you could go from there. And then this one right here, when y equals 0, if I set that equal to 0, now this is, again, graph it and trace it all you want. With that step size of 0.1, you can tell me when it's in quadrant 1 by looking, and that's fine. But if you set it equal to 0, you can find those key elements. So that one would have been, ooh, when's that one 0? 1? Just 1, right? Time equals 1. And that's what we got. Set equal to 0. That would be your x-intercept, because that's not in quadrant 1. It's kind of on the border of quadrant 1 and 4. And we got the t equals 1. What those play out as is they just tell you these 2 key points that we found manually. They just get you there a little bit faster. And that's fine. Your interval is about what t's land you in the right quadrant. Okay. There's some other cool tricks, but that's all that parametric graphing is you plot points x and y, but you have to put t in to decide when does it hit there. And negative time, I'm using time as a basic idea, but negative time is okay in this context because it's just a helpful hint. Time is something we're all familiar with, so that's why we use it. All right, we get out at 48, right? So there's this guy Stuart. He shoots an arrow straight up from the top of a building, which is a really dumb idea. Golly, Stuart. Can you find some other hobby? So he shoots it with a velocity of 245 feet per second. That's got, now just to give you some context here, this is where we're going to pick up tomorrow. 245 feet per second in miles per hour. We need to know this. Come on, Google. Do your magic. It says resolving host. Resolve you. Come on. It's not. You said that so soft. The computer didn't hear you. Say it louder. What? There's no internet? We just want this. Come on. There is internet. Well, if we can convert that, if I had internet, if you have your Googly at your hand and you can make this happen, ask Siri. That might be good. But in the meantime, what we have is this formula that allows us to see or calculate these, and I'll show you. And you don't have to memorize it. You just have to know how to use it. Okay. Turns out, when you guys shoot an arrow or anything that's a projectile, there's an x component and there's a y component, if you want to look at it that way. And somebody has developed this. It's actually trigonometry to develop it, so it involves a little trig. But this is just to give you the idea of things and their components. So sometimes you want to know how fast it's moving in each direction. Okay. Now, the y component has this crazy little thing called negative 16 t squared if you guys have done a little bit of physics, there's negative 16 has a magical property. It's something, whoopsie. And then plus, there's the sine thing. I'm going to put in there v naught. Of theta times t. And then there's one last piece of it that I have to squeeze in there. Plus y naught. I mean, why not? Okay. Now what I'm going to do for you, because this is just the arrow shooting straight up. With this situation, if you're shooting straight up, there is no x velocity. Without giving you a formula, I just want to say, did you know that if we're going straight up, it's only moving vertically? And if there's no wind, because we're in a perfect world, in a lab, in a vacuum, and you're wearing a spacesuit, shooting an arrow straight up so that you pierce your spacesuit if you let it land. Oh, this is just dumb. But anyway, you got no horizontal velocity. But you do have vertical, and it's mounted by this crazy thing. This theta is your initial angle. So straight up, 90. Yo. And then v naught is initial velocity. And then since we're doing the negative 16, this is a feet per second measure. This is gravity due to acceleration at 32 feet per second. This is negative 16 is a direct relation to 32. It's half of it for a good reason. I'll show you tomorrow. But initial velocity in feet per second. Okay. Remember, the bell actually rings at 49, so technically at 2 minutes. And then why not? Because why not? It's the initial height. Oh, poop. Okay. So we have a formula, and then you will always have this. I'm never going to make you memorize this. It's just being able to take the components. The x and y components, they're derived from known formulas about gravity and motion. I can tell you its y location at any given time, how high it is. Okay, so the vertical thing. All right, so it says write the parametric equations, which we will shortly. We've effectively done it. We just need to put numerals in there. Good work, y'all. Send that to your mates, and we're off and running. There will be my math lab coming up, and it's due toward the end of the week. And it has a few of these real short ones. And if you want to work ahead, you now have access. You'll get what's being explained. And there's a lab day in there somewhere. I gotta look.